recording the session. Okay, asymptotics. So the idea is to extend the notion of limit for sequences to the random variables. So you are going to treat the random variable as a sequence. Actually, you have a sequence of random variable depending on n. N is sample size, and you will observe the behavior of the random variable as n goes to infinity. Okay. We already know the definition of sequence, right? So suppose you have a sequence an, and n is some positive integer, right? You can define an as 1 divided by n, for example. And obviously, a1 is going to be equal to 1, a2 is going to be equal to 1 over 2, and so on and so forth, right? So this is the basic sequence that we had in calculus. Now we are going to extend this to the random variables. Particularly, suppose the sample mean is defined by summation of xi's divided by n. Right? Obviously, this sample mean, it is a random variable because it is a function of the random data, random variables, xi's, and we are going to look at the behavior of this quantity of this random variable xn as n goes to infinity, right? But in doing so, we have to think of types of convergence here, right? I hope you remember from basic calculus that in this case, this limit is, I mean, there are conditions when the limit converges and when it is diverges, it is diverging. But here, when you're trying to apply it to random variables, it is really, I mean, you cannot say that, you cannot always say that there is a single value where this limit is converging, isn't it? Even if n goes to infinity, you cannot say that this is converging, this sequence is converging to some specific value. Yes. So here you have to define specific types of convergence for random variables. There are 4 types of convergence in statistics. We are going to deal with 2 of them. And obviously, the notion of limits can be extended to random variables in a straightforward manner. So there are 4 of them, as I've mentioned: almost sure convergence, convergence in probability, mean square convergence, convergence in distribution. Okay. Now let's look at definition 6.1. Suppose you have a sequence of xn, which is sequence of random variables, and we say that xn converges in probability to x if for all epsilon greater than 0, this limit equals to 0. So what does this mean? It means that for any epsilon that you guys give me, I can come up with some n for which the probability of this animal, probability of the absolute value of the deviation of xn from x greater than epsilon is actually equal to 0. You see here, there is a little bit of difference here. When you say xn converges to x in probability, xn itself and x itself, you know, xn itself is some kind of random variable. So you are talking about the behavior of this probability in the limit. You are not talking about the point-wise convergence, as we were, I mean, as is the case in, for example, sequences. Right? Usually we write it in this way. We say xn, sequence of random variables xn, converges in probability to x. This is a shorthand notation for what is written here, right? Alternatively, you say pelim xn is equal to x. And we have several properties there. So if you have probability limit of xn and yn, then the summation of these two sequences will converge to the sum of their limits in probability. Okay, and if x is, you know, if you have convergence of xn to x and there is some a which is constant, then obviously a times xn is going to converge to ax. So we have additional 1. So suppose you have see here the random variable is converging to a constant value, and suppose you have continuous function g at a, then g of xn is converging to g of a. This is actually called continuous. This is kind of continuous mapping theorem. Okay, but the same holds for product of two sequences. Okay. Yeah, we're going to use this animal for the proof of law of large numbers. We know that according to Chebyshev inequality, the probability that xn diverges from mu by a value greater than epsilon is always less than or equal to variance of xn divided by epsilon squared. Actually, this absolute value of epsilon is redundant here. Actually, it's epsilon squared, that's all. So if this is the case, we can prove the so-called weak law of large numbers. What does it tell you? It tells you that if you have a sequence of IID random variables, remember IID is important keyword here. Okay, you have IID random variables, sequence of IID random variables, and all of them, they have common mean mu and common variance sigma squared, and variance is finite, less than infinity. Yes. So if that is the case, if you define xn as here something is missing, it should be I. So this if you define xn as the average of the random variables, then xn is guaranteed to converge to mu, to the mean, in probability. And how you do it, it is very simple, in the sense that you see if you have x's, I should say xi suppose x how's it written? So you have sequence of random variables where expectation of xn is equal to mu and variance of xn is equal to sigma square for each x, I mean. Then if you start summing them, if you take n x's, if you look at this quantity and define it as x bar n, then we know that expectation of x bar n is going to be equal to mu, exactly. And the variance of x bar n is going to be equal to sigma square x of over n, yes? The number of random variables that we are summing. So this is the variance. Right, and then using Chebyshev theorem, we know that the probability that x bar n minus mu greater than or equal to epsilon is actually less than or equal to sigma square over actually sigma square n, because x is, the variance of xn is x bar n is actually sigma square over n divided by, so this is the variance divided by epsilon squared, right? And you can rewrite it as sigma square divided by n times epsilon squared, right? So we know that the upper bound of this probability is actually sigma square over n times epsilon squared. If you want to take limit as n goes to infinity, probability that x bar n minus mu is exceeding epsilon, that is obviously going to be equal to a limit of n goes to infinity sigma square over n times epsilon square, right? And look at this quantity, please. So sigma square is a constant value, right? Epsilon also is a constant value, okay? It's arbitrarily close to zero. Positive value arbitrarily close to zero. For example, let's say 0.5, 0.1, 0.001, doesn't matter. So what changes here as n goes to infinity is n here, right? So what happens if n goes to infinity in the right-hand side of this equation? Obviously, once you do that, the limit is going to be zero, because once you divide a constant value, sigma squared, by a large n, the limit is going to be zero, right? So this is actually telling you that. So I can now delete this part, and I can say that the limit of this guy, the limit of this animal, is actually equal to zero, which is the very definition of convergence in probability, right? So it means that you can alternatively write it as this. You can say that x bar n is converging to mu as, so in probability, as n goes to infinity, right? That is what we mean here. Okay. So probably what I have to, probably the definition was a little bit wrong here. I should have said that you have xi's, so you have a sequence of xi's and i's in n, right? So that would have been a better definition, because we are not using. So you have xi's, sequence of random variables, x1, x2, xn, and then you are taking the average and define that average as x bar n. Okay. So this is the this property. So this property is actually called law of large numbers. What does it tell you? It tells you that if you have a sample mean, so by definition, x bar n is the sample mean, right? Because when you are taking random sample, you actually, if you are taking random sample and finding the average of the sample, you are effectively, calculating this quantity, right? Isn't it? And this means that, this finding means that as n goes to infinity, sample mean is actually converging to the population mean in probability, okay? And that is called the law of large numbers. And that is an important result. Why is it an important result? Because in reality, suppose you want to find the average CGPA of ADA students, all right? So you have many students studying at ADA, right? Look at it. So this is the population of ADA students. So there are many, many students. And you want to find the mean. You are interested in the mean parameter of this population, mean CGPA of ADA students. But there are many students studying at ADA, and it is not easy to collect data about each and every student there. So if the law of large number is correct, then what you can do is you can take a random sample, so which is a subset, strict subset of the population, right? And then compute the sample mean. You know, this sample mean is going to converge to the true population mean in probability. It means that this is going to be a good approximation. This is what it basically means. It means that x bar n, the sample mean, is going to be a good approximation to the true population mean, given under which conditions? Given that you have random sample, so you have random choice of students to your sample. Second, we are assuming that sigma square of population, the variance of population, is finite. So basically, given these conditions, that you have IID random variables with common mean and variance sigma square, then sample mean is going to be a good estimator. This is how we call it. It is going to be a good estimator of the population mean because it is converging in probability to the true mean. Okay. Now let's have a look at example 1. Suppose you have random sample from a distribution with common mean mu and variance sigma square, as supposing that sigma square is finite. Okay. And we have to show that the sample variance is a consistent estimator of variance. So what we have to do here is, let me check my solution to be fast. So let me add one more page. This is example 1. So we say xi minus x bar square over n minus 1. This is actually our estimator, yes, sample variance. So we know that summation, obviously I goes from 1 to n. Now let's prove that xi minus x bar square is actually equal to what? You can say that this is equal to xi square minus 2xi x bar n, let me put n here, plus x bar n square, right? Then you can simplify it as summation of xi square, then minus 2 times x bar n times summation of xi and plus summation of x bar n square. You see, the summation is such a symbol that, you know, such an operator that you can apply it to each and every element separately. So I applied summation on xi separately, then 2 times xi x bar n, and then to the last element x bar n square. Okay, you can do that. And then pay attention to one fact. If I divide the second term by n and multiply by n, nothing is going to change, right? So let me write it here. If I divide this animal, by n, and multiply by n, nothing is going to change, but this guy is going to be actually equal to x bar n. So then what I receive is, I receive summation xi squared minus 2 times n times x bar n squared, right? Plus, and I know that this guy is a constant, x bar n is a constant value, so I can write it as, if I'm summing it from 1 to n, I can rewrite it as n times x bar n squared. So as a result, I receive summation xi, so I have sum over i's, xi squared minus n times x bar n squared. So this is what we receive here. Okay, so the numerator part of this is known to us now. Then we can say that s squared is equal to summation of xi minus x bar n squared over n minus 1, and that is equal to, by definition, summation of, I goes from 1 to n, xi squared minus n times x bar n squared over n minus 1, right? Now let's take the limit of it. What will happen if you take the probability limit of it, okay? Meaning that what is the deviation of it from the true variance, okay? So by definition, we know that x bar n is actually, by law of large numbers, x bar n is going to converge in probability to mu. And we know that x bar n squared is going to in probability, it is going to approach to mu squared, right? And this means that, again, by law of large numbers, 1 over n sum of xi squared is actually going to converge to expectation of xi squared, which is equal to mu squared plus sigma squared, right? And what else? We know that. So let me, probably I had to rewrite it in this way. Just a minute. Okay. So we said that s squared is actually equal to summation xi minus x bar n squared over n minus 1, which was equal to 1 over n minus 1 times summation xi squared minus n x bar n squared, which is equal to n divided by n minus 1. I do some manipulation here. So I basically multiply every side by n and like each element by n and divide by n, right? So I can rewrite this equation as x bar squared, right? So I know that the limit of this, so let's look at the limits of each animal separately. So the first animal here is, so limit n over n minus 1. As n goes to infinity, this is obviously going to approach to 1, right? So by law of large numbers, we know that this animal, x bar squared, if you take the limit, let me write a shorthand notation. So the probability limit of x bar squared is actually mu squared. Yes, so then I also know that, so by law of large numbers, I can apply law of large numbers. I know that the average, sample average, is approaching to, is converging to the expected value as n goes to infinity, meaning that I know that summation of xi squared, treat this xi squared as a random variable, yi, no problem. I know that this, by law of large numbers, it should converge to the expectation of this thing, right? I know that. So let's compute the expectation of this thing. If you compute it, it's going to be equal to sigma squared plus mu squared. Now let's plug everything back. So we know that in the limit, the probability limit of this whole thing, the probability limit of this whole thing in the rectangle is going to be equal to the individual probability limits multiplied by each other. I mean, you just replace the terms by their probability limits. N divided by n minus 1 is replaced by 1 times sigma squared I, sigma I xi squared over n is replaced by sigma squared plus mu squared, and x bar squared is replaced by, I should say n, by mu squared, right? And then I receive sigma squared. So this means that as n goes to infinity, indeed, the sample variance is going to approach to the correct variance, the true variance of the random variable, and that is called consistency property, which means that as n goes to infinity, the sample, so the estimator converges to the parameter value in probability. Okay, that is the definition of consistency property. So you have an estimator. Again, the estimator is this. Here in this case, we're interested in this parameter mu, for example, and you take a random sample and compute the sample mean, which is the sample analog of the population mean, right? So you know that as n goes to infinity, you will get probability limit. Alternatively, you can apply the same idea to population variance. So you have some population, you are interested in the income of ADA students, actually in the variance of ADA students' income or height, let's say. You cannot collect data about each and every student. You are taking a random sample. Okay, this random sample is a strict subset of the population. Why it is good? It is good because it has less elements, and you can compute the sample variance. Okay, and we know that we have proven that the probability limit of this estimator. So remember, S squared, the sample variance, is an estimator of the population variance, meaning that this is a good approximation. It is an approximation of the true variance of the population. Okay, and we know that as you increase the sample size, S squared is going to converge to sigma squared, true variance, in probability. Okay, and this property of estimators is called consistency, or EN property. That's large sample property. You increase the sample size and you converge to the true parameter value in probability. Okay, and the definition of convergence in probability is given here. So the definition is that the probability that the estimator value differs from the parameter value by epsilon in absolute value is equal to 0. That is the convergence in probability. Okay. So remember, this law of large numbers is an important concept. You have to know that. So what else is left there? There is something else. No, we have already shown that sample variance is a consistent estimator of the population variance. Now let's look at the second, a less restrictive version of convergence of random variables. That is called convergence in distribution. So again, we are supposing that you have some sequence of random variables, okay? And you have this f is CDF of xn and CDF of x, okay? So we say that xn converges in distribution to x if the CDF of xn is actually equal to, in the limit, it equals to the CDF of x. Okay, and we write it in this way. We say that xn converges to x in distribution. Okay, this is the difference. Or you can say that x is the limiting distribution of xn. Okay, the same things apply, the same properties that we discussed in the previous case is applying to convergence and probability in distribution. And remember that convergence in distribution, convergence in probability implies the convergence in distribution, but not vice versa. Okay, these things are kind of standard. You have two, you have kind of three sequences, A, B, X, and each of them are converging sequences. If that is the case, you just replace, you know, their limiting behavior is determined by individual limits. Okay. Then what we get is we get some important, yet another important theorem that is called central limit theorem. Central limit theorem is telling you that if you have, you know, a sequence of random variables which are IID, independent and identically distributed random variables, with common mean and with common variance, where variance is finite, then the sample mean minus the population mean, true mean of the population, or true mean of the random variable x, you can say. Okay, random variable x's mean multiplied by square root of n, square root of the sample size, that is going to converge in distribution to normal distribution with mean 0 and with variance sigma squared. Okay, there is an alternative way of saying it. If this is the case, we know that the linear combination of normal variables is still normal. You can also say that n square root of n times x bar n minus mu over sigma is actually standard normal. It's converging to standard normal in distribution. Okay, this is an alternative way. Or if you want, you can also take this square root of n and put it here. This is more standard version. I mean, nothing changes here, right? They're identical, equivalent mathematically. Okay, and what is good side about this? Why is central limit theorem is so important? The importance of it is that it does not make any distribution assumption about the x's. It doesn't tell you that x's should be normal, irrespective, regardless of the distribution of x's. You see, as long as they are IID with common mean mu and with common variance sigma squared, we know that this property is going to hold, and that is very strong. That is very important thing in statistics. You see, you can always compute probabilities regarding the sample means using the normal distribution, standard normal distribution. That is really important because normal distribution is something that we like to work with, right? Now let's look at the second example where we have to apply this property. Suppose that xi's are IID Bernoulli random variables, okay, and probability of success is 0.25. I have to find the approximate probability here. Remember, it is approximate because you see original distribution of x is Bernoulli, But we're sure that as n goes to infinity, the sample mean is going to be normal. I mean, it will converge to normal distribution, right? It will be approximately normal. That is how we call it sometimes. The distribution of this sample means is going to be approximately normal as n goes to infinity. So we can basically compute the probability related to Bernoulli random variables using the normal approximation. That is really a strong thing. I mean, strong tool in statistics. Okay, give me a second, please. Okay, let's solve example 2. So we know that xi is Bernoulli with probability of success equal to 0.25. So this means that the expectation of xi is actually equal to 0.25, and the variance of each xi is equal to 0.25 times 0.75, right? If this is the case, based on central limit theorem, we know that x bar n minus 0.25, which is the mean, times, so and we have 100 observations. We know that x bar n, so let me write it in this way. We can say that, so apply CLT, square root of 100 times x bar n minus 0.25 is going to convergent distribution to normal distribution with mean 0 and with variance equal to the true variance of xi's, the variance of xi's, right? And that's all. Right? And then what we can do is, we are interested in the probability of, and you can do manipulation. You can actually find the approximate distribution of x bar n here. This is going to be equal to a convergent distribution to normality with mean equal to 0.25, with variance equal to 0.25 times 0.75 divided by 100. I mean, it's, if you remember, we said that linear combination of normal variables is normal. You can suppose that this is a random variable y, and you can basically manipulate with y and receive the distribution of x bar n using the function. It's very easy. Yeah. I mean, you can do it in this way. You know that the expectation of y is equal to the expectation of square root of 100 times x bar n minus 0.25, right? and you know that this is equal to 0, right? And I know that I can take the expectation operator, like I can write it as square root of 100 times expectation of x bar n minus square root of 100 times 0.25. Right, this is the so this is, and this is going to be 0. We know that this is going to be 0. Then we can basically find that the expectation of x bar n is going to be 0.25. It's easy, right? And then you can do the same thing, and you can find the variance in that way. So I don't want to spend time on that. Anyway, we have received the distribution of x bar n. After you received it, you can say that you can easily compute the probability. We have to compute the probability that, let me see which probability we are computing. You have to compute that probability that x bar n is less than or equal to 0.2. Okay, so this is now very easy, because to find the probability, you have to know the probability distribution, and we know the approximate probability distribution at least. So x bar n less than or equal to 0.2 is actually, it can be, you can apply the standardization technique. You can say that probability of x bar n minus mu over, so minus 0.25 over, okay, just convert it to, I don't want to spend time on this. Just say that this is z. Yes, if I apply standardization on x bar n, it's going to give us z. So I have applied standardization on the left side of the inequality. I have to do the same in the right side. So it's going to be equal to 0.2 minus the mean, which is 0.25, divided by the standard deviation, which is equal to 0.25 times 0.75 over 100. Okay, and then this gives you what? This gives you probability of z less than or equal to minus 2 over 3. And then you have to look in the z table and find this probability. Okay. And if you want to, obviously, if you want to find the exact probability, you can also find, if you want, you can also find the exact probability. Maybe I should say this is approximate. So the exact probability without normal approximation actually can be found using this is actually the same thing as saying that probability that summation of xi over n is less than or equal to 0.2. And n is 100, obviously. So let me write 100. So this means that you are actually interested in the probability of, so the sum of xi's obviously is going to give you the sum of successes, the number of successes in 100 trials. So you basically want to find that the number of successes in 100 trials is actually less than 20. Is less than 20. Yeah, it's going to be normal approximation is actually coming at handy here, because for this you have to, because this is discrete probability mass function, so you have to compute it. You have to sum each point probability here. It's going to be a bit messy, and it's going to take a long time. So you have to find, this is Bernoulli binomial probability here, obviously. So you have to compute the probability that x is sum of x's is equal to 0, then up to sum of xi equal to 20. This is a little bit burdensome to do it. So therefore, normal approximation is actually saving us a lot of time at this point. Okay. Yeah, we have yet another method, which is called delta method. It's actually applicable when you have some function, okay, so some function g, which is differentiable at point theta, at true parameter value. In that case, you say if xn is a sequence of random variables, you can say that according to delta method, you know, g of xn minus g of theta is going to be approximately normal, okay, with this mean and with this variance. Now let's see which example we have here. Example 3. So we have NIIT. So here we have xi is normal and IIT with mean 2 and with variance 1, right? What we are looking for is, we are looking to find the probability that y is less than 3.7, and y is defined as square of x bar n, okay? So n is 100, x bar n is actually equal to xi, I goes from 1 to 100 divided by n, and y is equal to x bar n squared. So we want to find out the probability that y is less than or equal to 3.7, if I'm not mistaken. Yes. So for this, remember, to find the probability, you have to know the probability distribution, obviously. So how can we find the probability distribution for y? Y is actually a function of some normal variable, right? I mean, that is not really important to have normality here. As long as you have IID, that is okay. So G function is actually, G of A is actually A squared. Okay, G function is just square function. So we know that square root of n times G of x bar n minus G of theta. Theta here is actually the mean. Is going to be approximately normal with mean 0 and with variance equal to sigma squared times G of mu squared. Okay. Or alternatively, you can say that you can use the same logic as we have applied previously. You can say that G of x bar n is actually going to be normal with G of mu and variance equal to sigma square of n, sigma square over n times G prime mu squared. Now, instead of x bar n here, we have, instead of G here, we have square function, and this guy is actually equal to y. Yes, y is equal to G of x bar n, which is normal, right? And for that, we have to find G of mu. And before we have to find, so we know that the mean is equal to 2 and the variance is equal to 1. So we can say that y is actually approximately normal. So G of mu is going to be equal to 2 to the power 2. And sigma squared here is going to be equal to 1 over n is equal to 100 times if you take the derivative of mu square, so derivative of mu square is actually equal to 2 mu. And mu is equal to 2. That gives you 4, isn't it? And you have to square that thing. So it's going to give you 16. Okay. So according to the delta method, y is going to have this distribution, approximate distribution. And let me write 4 here instead of 2 to the power 2. Okay, now it's easy to find the probability that y is less than or equal to 3.7 because you can convert it as long as you have normality here, at least approximate normality here, based on CRT, based on delta method actually. You can say that probability of y can be written as probability of z being less than or equal to 3.7 minus 4 over square root of 16 over 100. And that is equal to probability of z being greater than, you have to make some manipulation here, 3 over 4, which in the end gives you 0.22. Okay, this is example 3. Now, example 4, suppose you have sum of two variables, et and et minus 1, and both of them are IID with mean 0 and with variance 1. Now we have to show that x bar is actually converges to 0 in probability, and we have to find variance of x bar n. Okay. Okay. Example 4. Where et and et minus 1, they are IIT with 0 mean and with variance 1. Great. In that case, what you have to do is you have to show that x bar n converges to 0 in probability. So we know that according to law of large numbers, if you take the x bar n here is actually what? X bar n is actually equal to xt t goes from 1 to n, let's say. Instead of I, we have t index here. Divide by, let's say, n, and that gives you x bar n. Okay. So we know that according to law of large numbers, this guy is converging to expectation of x bar n. We know that. So basically what we have to do is we have to find x bar n. So the expectation of x bar n. Expectation of x bar n is actually equal to expectation of, just plug the definition, summation t goes from 1 to n, x over n, and then just plug for xt, that gives you summation of epsilon t minus epsilon t minus 1, t goes from 1 to n, And we know that expectation and summation operators, they can be interchanged, and we can rewrite it as summation of expectation of epsilon t minus expectation of epsilon t minus 1. T goes from 1 to n over n. And by definition, both of these variables, they have expectation equal to 0. As a result, the total expectation is going to give you 0. So it means that indeed x bar n has its probability limit equal to 0. So this part is kind of proven. The second thing is, we have 8 minutes left. So the second thing is P part. We have to show that we have to find what? Yeah, we have to find the variance here, and it's very simple. All right, because we know that according to central limit theorem, you know, according to CLT, we know that square root of n times x bar n minus mu is actually approximately normal, right? We know that, isn't it? So here we have found that mu is equal to 0. We have already found that. So what is left is square root of n times x bar n, then is distributed approximately normally with mean 0 and with variance sigma square. Now the problem is to find the sigma square. Finding sigma square is basically to find the expectation of actually the variance of xt, right? And the variance of xt is equal to variance of epsilon t plus epsilon t minus 1, which can be rewritten as variance of epsilon t plus variance of epsilon t minus 1. And here, remember that normally we should have plus 2 times covariance of et and et minus 1, but as long as you have IID assumption here, independence assumption, so maybe I have to write it 2 times covariance of epsilon t minus 1. So this guy is actually gets equal to 0 and drops from the equation. And we know variance of epsilon t is actually equal to 1 by definition, and the same goes for epsilon t minus 1. So as a result, you receive 2. So it means that instead of sigma here, you should have 2. Okay, as simple as that. So we have 5 more minutes left. Finally, we have 5th question. You have means of 2 independent drawn Bernoulli labels, and each have probability of success equal to 0.5, and the same size, sample size. We have to approximate this probability that x bar 1 minus x bar 2 is less than 0.1 in absolute value. Actually, we have to define actually the n here. It's the inverse problem here. Okay. So for that, what we have to do is we have to, obviously, when we are dealing with probabilities, you have to find the probability distribution. Right? Okay. So we're interested in probability x bar 1, x bar 2. Just a minute. I forgot the question. So x bar 1 minus x bar 2 is less than 0.1 is equal to 95%. Okay. And here we have n's. So we know that xi's are Bernoulli with 0.5. It means that the expectation of xi is equal to 0.5. The variance of xi is equal to 0.5 square, right? By definition. If that is the case, then x bar 1 is going to be approximately normal, with mean equal to 0.5, with variance equal to 0.5 square over n. And we don't know n. The same goes for x bar 2. The same goes for x bar 2. It will have approximately normal distribution with 0.5 mean and with 0.5 square over n variance. Then we can define another variable y. So let's define this x bar 1 minus x bar 2 as y. So y is equal to is equal to x bar 1 minus x bar 2, and it will have an approximate distribution. We know that linear combination of normals is linear. You can apply the continuous mapping. Actually, there was a theorem like that. So just replace this. So the expectation of x bar 1 is 0.5, and the same goes for x bar 2. So as a result, the difference is going to give you 0. And the variance of this quantity is going to give you 0.5 square over n times 2, because they are IID, so you have to sum their variances, individual variances, and covariance is equal to 0. Now, after we have this after we have the distribution for y, it's now easy to find the probability that y is less than 0.1 is equal to 0.95. Actually, let me add n here. So let me just check whether it is correct. Okay, less than 0.1, yes. Okay, now what you are going to do is, so you're searching for such an n, that this equality holds. Okay, and if you have, suppose you have normal distribution, okay, and the center is at 0. So here you have 0.1, here you have minus 0.1. So basically the idea is you are trying to find n such that this probability is going to be equal to 0.95. Okay. You can say that the probability that actually so we know that the quantile value, if you standardize this thing, you can write it as probability of minus 0.1, so minus mean, divided by what is the standard deviation is this, so square root of 2 times 0.5 square over n, less than z, less than 0.1 divided by square root of 2 times 0.5 square over n, right, equal to 0.95. And we know that the quantile value that gives you 95% probability on the standard normal is actually equal to 1.96. Okay, so basically you are equating this 0.1 over square root of 2 times 0.5 square over n equal to 1.96, and then you are computing n here. Then n should be equal to what? Square root of n is actually going to be equal to 1.96 over 0.1 times square root of 2 times 0.5. Okay, and then you can square it again. You can say that n is actually equal to 1.96 over 0.1 times 2 times So everything squared. So it is approximately, it's something like 200. So n should be at least 200 so that you could get this probability equal to 0.95. Okay, that is the last example. Okay. Now, what is the problem?